2.5 inverse functions. We'll just really quickly go through this. The inverse of a function undoes what the other function does. I feel like that's the worst sentence I've ever written. Do you get what it's saying? Basically, they're total opposites of one another. So, you know, we first learned how to add, then you learn how to subtract, and then do it. Multiplication, and then division, and on and on. So these are opposites of one another in a sense. So to find the inverse of something like y equals f of x, step 1, we check to see that f is a one-to-one function. We'll talk about that using examples. Step 2, replace f of x with a y. I'll show you that with an example. Step 3, we swap the x and the y values. Step 4, solve the new equation for y. And step 5, replace y with this notation. It looks like f to the power of -1. That's this new notation that indicates that it's an inverse function. So it's showing the inverse of f of x, essentially. So let's dive into an example so we can see what this would actually look like. So going through this, well, for starters, f of x equals 4x plus 1. What kind of function is that? Linear function. So do you see already off the bat, if it's a linear function and the slope is 4, which quadrant would it end up pointing in? In quadrant 1. So if it's at a slant, do you see obviously it's a one-to-one function? To remind you, a one-to-one function has to pass the vertical line test and also the horizontal line test. So it can't have like double y values or double x values at any point. That's all it's saying. So we're good to go for the first part there. The next step is we would take this and we would rewrite this to say, I'm having troubles with where I should do this. I'm going to move it down here. Y equals 4x plus 1. So I just swap out the function notation, rewrite it using y. So not a big deal if we don't. It's just easier for us to work with it that way. And then we're going to swap, not that, we're going to swap these two. And instead I'm going to say this is x equals 4y plus 1. So we're just going through that step-by-step method that I had written at the start. We swapped the x and the y. And now that we've swapped the x and the y, we just start manipulating and using our algebra skills to get the y by itself. This is all stuff we know from before, so I don't feel the need to explain it all. I know you all know how to do this. We'd get x minus 1 equals 4y, and we could just divide this all out by 4 to leave us with just y. And to do this appropriately, we can rewrite this in function notation using the inverse of f of x is equal to this x minus 1 over 4. Or I could change it to a quarter x minus a quarter. Whatever, the format doesn't really matter, but we want to be able to use these skills to find the inverse, which is what we were looking for. Is this review? Last year? You know things are bad when you don't know, and I don't know either. Oh well, now you know it. Do you know it now? Okay, good. That's good enough. Are we good to move on then? Well, maybe I'll first tell you and just explain it, but if we wanted to check to see, like, you don't need me to mark your work. How could you check to see if what you've done is correct? If they're total opposites, think of what we just did. What should we be able to do? They're total opposites. Do you see I could either plug this new one into the original and have everything cancel out? Or the other way around, I could plug f of x into the inverse x and have everything cancel out. Because if you think of what we just did, we swapped them and found the complete inverse or opposite. So, verification to check to see if this is right looks like some of the stuff we did a few lessons ago, the composite function stuff. So if I say f of g of x, so I'm going to call the inverse notation, let's say I called that g of x instead of having to write out the inverse, then everything would cancel out and just leave me with x. So if I took out the function notation, essentially this is saying y equals x. And if I swapped it the other way, so I use this g to represent the inverse, g of f of x, so if I plugged in the original into the inverse, everything would cancel and we would just get x, just like in the other one. Because they truly are opposites or inverses of one another, everything ends up canceling. So let's take a look at what that looks like or what I mean. We could check the work we just did. That looks like chalk. Check by plugging it in. So if I do f of, and maybe instead of g of x, I'll use the actual notation so you can see what I'm talking about. My inverse, if I look back here, I found was x minus 1 over 4. So I'm going to write that down in here. I feel like it's too small if I try to show you that as well. So you can look back in your notes if you want to. But basically I'm just saying this part is just this part. Or it's what I call g of x up here, or the g up here. Are we good with all the swapping, substitution of this notation and what I'm referring to it as? Okay, so then according to this, I'm wanting to plug in this x minus 1 over 4 into our original equation, which was 4x plus 1. So what that means is 4, and instead of x, I'm going to do that, plus 1. So instead of x, according to this, I'm plugging in that x minus 1 over 4. Do you see why we learned about that composite functions and how it ties in with this? So here we would do what we normally do, and that is wanting to cancel out whatever we can and simplify. And you see here I have x minus 1, and at this point the brackets could be gone, plus 1, so those are also gone. So after working our way through all of this, we can see, so therefore, after doing all the work, f of plugging in the inverse of f of x just ends up canceling everything out to give us x, which is how I know, or I can check to see that it in fact is correct. So if it asks you to find the inverse and verify your solution, this is how you verify your solution. You just take what you found and you plug it back in, and it's totally your choice. We did f of the inverse. You could do the other way around. You could take your inverse and you can plug your original into it. And I would say when making your decision, just pick the one that's going to be easier to work with, right? Sometimes one's a little bit easier. Are there questions about that so far? Pretty okay so far? Okay. The domain of f of x, then, is the range of the inverse of f of x and vice versa. Does that make sense when you think about it? If we had our original f of x and we looked at the x values or the domain, that becomes the range of the inverse because of what we do. We're swapping the x and the y values, so that makes sense. So this is, you know it's important when I put a star and maybe even a box around it, because you'll be asked about this. So it's important to know and understand where that's coming from. Okay, if we have this function g of x equals root x plus 5, we want to determine the inverse of it and verify the answer. So Here's the second example where we'll again go through those steps. Let's just think about this. The first thing is always, is it a one-to-one function? So, you know, like that would not be a one-to-one because it wouldn't pass the horizontal line test, right? What does root x plus 5 look like? Is it a one-to-one function? Yeah, it looks kind of like that, right? So is it a one-to-one function? Would it pass vertical? Yeah. Would it pass? Yeah, we're good to go. So we're fine with that. Then we can take it and rewrite it to say root x plus 5 equals y. We swap the x and the y. So x equals root y plus 5. And then we just want to get y by itself. I know I'm flying through this, but am I right that you already know how to do this? We want to get rid of the root sign, so we're squaring both sides. So I'd get x squared equals y plus 5. And then I just want y, so x squared minus 5 equals y. And I'm sorry, I'm going to squeeze it in. Actually, this is why I love this thing. I'm going to take this all and I'm going to move it over. Do you see why I love this thing? Isn't that amazing? Because I just realized we have to verify and I didn't leave room for that. So, rewriting this properly, we would say the inverse of g of x equals x squared minus 5. So there's the first part of us answering the question. And then it says verify. So it doesn't really matter how we do this, but I think it might be easiest if we just plug this back into the original. So we could say g of the inverse of g of x equals, well, I'd go like this, and instead of x, I'm just going to go like this and say plus 5. So far, so good. Then, if I found that the inverse is equal to this, that's the part that I'm going to take and plug into the brackets that I've left here. So this x squared minus 5 am I going too fast? We're good? Okay. Do you see I don't really need the brackets, so we could just get rid of this. And magically, not really that magically, we knew this was going to happen if we had done this right. We just end up with the square root of x squared. And so the fact that it ends up giving us x shows that we've done this properly and that we verified that that in fact is the inverse, that x squared minus 5. Questions? Okay, using the same equation, determine the domain of the inverse of g of x. Determine the domain of the inverse. Okay. The domain of the inverse is going to be the same thing as what? Yeah, it's going to be the range of our original g of x. You get the reason for that, right? Because we're swapping the x and the y. So that's the reason for that. It's whatever you had originally gets swapped, the x and the y values. So this makes sense that they are like opposites of one another in terms of the x and y values. So let's go back to the original. You showed me like just going like this, you acted it out, what the graph looks like. What is the range on that original g of x? If you were to graph it out, what would I say the range is? And I'll put it in brackets here. Y would be greater than or equal to 0. Does that make sense to everybody? So then what is the domain for my new function, which I guess I'll do in blue so that we can keep things consistent. So therefore, what would my domain be if I write down my domain for this? The domain for the inverse of x, what's it going to be? If that's y is greater than or equal to 0, it's just going to be x has to be greater than or equal to 0. Good? Questions? Okay. Moving along. Okay, we literally do the same thing over and over and over again, but I think it's good to get some different perspectives, to see some different functions, some different equations. Do you remember what we call an equation like this h of x? What kind of function is that? Yeah, this is a rational function. We're actually doing a full chapter on these things. We're doing a full chapter on radicals. So it's good, I guess, that we're getting a little bit of exposure to it already. So if we want to take or find the inverse of this, we're still doing the same thing as before, but this time the equation looks a bit different. So first step, let's do y equals x over 2x minus 3. And I will say, like, yeah, maybe it's good that we're doing this together. There's a bit more going on here, so there will be a bit more to sort of work our way through. And that's the only way that this could maybe be a bit more challenging, or that it could potentially look a bit more challenging. But if you take the same step-by-step approach, I think you'll find it's not too bad. So there's the first step. Then what do we do with this? What's the next step always? Here's how it's a little bit different. We swap the x and the y values, right? So here's the reason why it's a little bit weird this time. Look what's happening here. X equals y over 2y minus 3. So we now have y at the top and at the bottom in our rational equation. Okay, so where do I go from here? If, like, the next step is usually to isolate y, what would be a smart next step to attempt to get to that point? Because right now that's not happening with the way it's written, right? Ideas as to what would make the most sense? Yeah, Leo? Yeah, we could multiply both sides by 2y minus 3, right? So we'd have x and then 2y minus 3 equals y, and that would cancel out the bottom. So it's like we took the bottom and just like multiplied it out at the top on the other side. So far we're good with that? Okay, and in doing that, well, again, we still want to get y by itself, so what would be another good, smart next move? Yeah. Perfect, thanks, Leo. So we want to multiply these out. So we would have 2xy minus 3x equals y. Good? The reason is, again, I feel like this is the theme in so much of what we do. We're looking for similarities and we're looking to get like terms together. So we really want to get the y's together because that's going to make things a little bit easier for us. So do you see that we could take this and move it off to the other side? Well, there's a few different ways we could do it, but that's one way we could do this. We could have y minus 2xy, and we can factor out the y. So when we factor out the y, we would have negative 3x equals y times 1 minus 2x. Oh, would have been smarter to do it the other way around so I didn't have the negatives to deal with. Can I backtrack and do that? Is everyone okay with that? Sorry, everyone who's copying down what I'm doing. Let's do this. Let's pull over the 3x and let's pull the y over here. So 2xy minus y equals 3x, just so we don't have to deal with the negatives at the end. We could, but this will just be a bit easier. And then we have y and 2x minus 1 equals 3x. And when we pull this up here, oh, I guess, wow, this is getting ridiculously long. Let's pull this up here. And we would get y equals 3x over that 2x minus 1 that we had factored out. And what was this? H. So it's going to be the inverse of h of x equals 3x over 2x minus 1. After all of that, we end up with our inverse function. It's just that we had a bit more going on in this scenario than we did with the others. Are we good so far? Now, it didn't specifically ask for it, but this is a good habit to get into. If we have a denominator that has a variable, what should we consider or write down when dealing with this? Yeah, what's the restriction on this? What is x not allowed to be? Can't be 1 over 2, right? Because we don't want 0 at the bottom. So really what we're doing is taking the bottom, setting it not equal to 0, and isolating, so x can't be a half. And we have our inverse. So the functions could change. It could even be other stuff. We've practiced a few of them. Just know that you still go through the same step-by-step procedure. So here's one where we have, what is this thing? If we were to sketch this out, what is it? Remember this thing? Is that a one-to-one function? No. So here's what we do. You know how step number 1 was determine if it's a one-to-one function? We know that this isn't because it's a parabola. It'll pass the vertical line test, but if I draw horizontal lines, clearly it's not going to pass. So what we can do in that scenario is I could just chop off half of it, or I could restrict half of it. So in working with this, I could say I only want to deal with the positive values. Or I could deal with the negative ones. It really doesn't matter. But we can still go through this procedure the same way. So I can still say, okay, y equals x squared plus 5. I can swap the x and the y. So I can say y squared plus 5. I do x minus 5 equals y squared. And then I can square root it to say root x minus 5 equals y. Flew through that, but you all know how to do that now, right? So do you see when I'm square rooting this, I technically could get plus and minus when I square root it? There's the part that we're interested in. So what I can say for this is in pink, so that'll be this part. That'll be the part that I've sort of indicated or shown here. So that's the part right here. If h of x, I feel like putting a box isn't the best thing. H of x, when x is greater than or equal to 0, then the inverse would be positive root x minus 5. And if instead I dealt with this negative side here, then that would be this, and that would be this part down here. So what do we do when it's not a one-to-one function? We place a restriction on it to make it a one-to-one function. Okay, so let's take a look at what the graphs of this would look like. If f of x and the inverse are symmetrical about the line y equals x. Remember that line y equals x is a diagonal line across our graph. It's this dotted line down here. And f of x is a reflection of the inverse of x over that line. So we've done reflections over the x-axis and the y-axis. This is now a reflection over this diagonal line y equals x. So if we had just a regular parabola y equals x squared, and I only, let's say, take the negative values. This is saying when x is less than or equal to 0. So for this part, let's say I draw it in this color here. We know that it would just be a function that looks like this. We've just chopped it in half. It's been restricted. I'm going to pick some point on here. I'm going to say that's -2. Then we know that that point there clearly would be 4. So -2, 4. I'm doing this for a reason. If that's the case, then my inverse, do you see that the inverse would be this negative root x? So if I did the swapping, isolating, etc., I'd get root x. But it could be plus or minus root x. But since we're dealing with the negative side that we've chopped, it would be the negative root x I'd be dealing with. And remember, when we're dealing with the algebra, we're swapping the x and the y values. So we would do the same thing when we're looking at graphs. If that point was -2, 4, can you tell me what the point would be on the blue graph? Without dealing with the equation, just by looking at the graph, what must -2, 4 become? Yeah, so it's going to be 4, -2. So it's actually going to be down here. So this would actually end up getting reflected at every point. Oh God, I just did a horrible job of that. But reflected, every point would get reflected from that point. So if I had done -1, 1 there, then this would be 1, -1 down here. And on and on. Like if I had done -3, 9, the new one would be 9, -3. So in every scenario, we're always swapping the x and the y coordinates to get our inverse function. So it gets reflected over that y equals x dotted line through the middle of our graph. This has been happening all along. I don't know if you saw it that way or picked up on it, but it's also going to happen all throughout this course. The graphing stuff is just another way to understand and interpret what's going on. It's the same as the algebra, right? It's just this way we get to see a visual image of what's going on, but it's essentially the same thing that we're doing. One last thing. Transformations in inverse functions. So this is combining everything, I guess, so far. If y equals f of x has the point mn, and it has an inverse y equals the inverse of f of x, that would become nm. We swap them, right? We just talked about that on the graph. If the point on f of x is mn, then the point on the inverse graph is going to be nm. We swap them. Okay, so then applying this, let's take a look at what goes on here. If I want to do this first question here, let me get rid of that. So if I want to do this one here, y equals the inverse of x minus 4, it will have the point, well, let's think our way through this. If the point on the original was mn, and I want the inverse of x minus 4, first of all, is that minus 4 going to affect the x values or the y values? Just the x values, so the y value is going to be the same. The y value in the original was n, but what is it on the mu inverse graph? I'm going to get rid of that arrow because I feel like that didn't help. Let's look at this as our inverse. So if we're dealing with, I'm way off with the colors today. If we want to do this to get our inverse point, do you see that the y value would be m? Instead of n, what's the new x value going to be? N plus 4. Make sense? So it's really just one new step, but everything else is the same as the stuff we've been doing. That one new step is that we swap the x and the y, and then we do the transformation part. So for this next one, my new point is going to be, well, what's my new x value? Does anything I know, I need to use different colors. So, for this one here, does anything affect the x values there? Nope. So what is my new x value? From here. It's still just n, nothing changes it. It is the inverse, so it is n, it's not m. And with this plus 5, what's the new y value here? M plus 5. So at the start, it maybe makes you think a little bit, but then you see it's the same old thing, right? With the new swapping of the x and the y. And for this last one here, for this one, okay, so there's a bit more going on there. Out of this, what affects my x values out of all this stuff here? The 2x. So instead of n, what's it going to be? If it says 2x, it's going to be 1/2, right? Or n over 2, whoever said that, right? Because it's the opposite of what we see. And how about instead of m, what's the y value now going to be? Just this part affects the y value, right? So it's going to be negative 3m. And there's your work.